Imagine a radio system as a pair of magic boxes that can send and receive messages through the air without any physical connection. This sounds fascinating, right? Now let's break it down further with real-world example. Think about the car radio you have likely tuned into at some point. It receives music, news, or talk shows that were broadcast from a large radio tower nearby. This interaction involves three main components. The transmitter. This is the big radio tower sending out the signals. The transmission medium. The invisible bridge that carries the signal. In this case, the air around us. Receiver. Your car radio, which catches the signals and converts them into the sound you hear. So it's like a magic, but it's all based on a science. The transmitter sends information encoded into signals through the air, and the receiver decodes these signals back into a form you can understand, like sound or data. Now, here's a visual representation: radio transmitter, air, which is signal pathway, and radio receiver. But you may ask here, what exactly is being sent through the air? It is a signal, a form of energy that carries the encoded information. What exactly is a signal? A signal is a way to transfer the information by changing some physical property. Now let's break it down with a few simple examples to make this concept crystal clear. Example number one. This is the flashlight signal example. So, picture this. It's a nighttime, and you and a friend are on opposite sides of a wide empty field. Your friend here sometimes needs your help, but how can they let you know? They decide to use a bright flashlight. Whenever the flashlight shines in your direction, you know it's a time to head over to help your friend. In this case, the flashlight is a transmitter, sending a signal by changing the physical property of light. Your eyes are the receiver, interpreting the signal as "come help me." The simple act of turning the flashlight on and off changes the light level in a way that delivers information, making it a signal. Example 2. The telegraph signal. Now let's go back in time to the era of old-fashioned telegraphs. In the system, a transmitter on one end of a wire alternates between sending electrical current and stopping it. At the other end, the receiver creates a beeping sound when it detects the current and stays silent when there's no current. Using a system like a Morse code, where patterns of beeps and silences represent letters and numbers, people could send messages across great distances. Here, the signal is based on changing the property of electric current in the wire. In the world of software-defined radios, we focus on radio signals, which are electromagnetic in nature. You might recall that from science class that electromagnetic waves can carry energy through the air. What makes radio signals so special is that they change the properties of these waves to represent information. But don't worry if this sounds too technical. You don't need to dive into heavy physics or math to work with SDR. Instead, we will focus on what kind of information radio signals can carry. Sound. Think of AM or FM radio, which carry music or speech. Video, like the shows and news on over-the-air television broadcasts. Control information. For instance, the signal from your car key fob that locks or unlocks your car. Data, such as the internet traffic your Wi-Fi router sends to your laptop or mobile phone, and much more. And here's the interesting part. All these types of information, sound, video, data, are themselves signals. They are essential quantities that change over time. To make radio signals useful, they need a way to connect with the information they are carrying. This is where modulation comes in. So think of modulation as a clever technique for embedding information into a signal, like putting a letter into envelope before mailing it. On the receiving end, the modulation extracts the information, turning the signal back into something meaningful like music, text, or video. By understanding how signals work and how modulation transforms them, you will unlock the power of SDR to communicate all sorts of information, whether it's music, video, data, or even commands to a drone. Now let's dive deeper and see how it all comes together. Now let's take a closer look at how a basic AM radio system works. AM, amplitude modulation radio, is one of the simplest types of radio communication, making it a perfect example to explore. So imagine a transmission tower at a radio station. So here's what happens step by step. Audio source. The radio operator starts with an audio signal. This could be music or someone's voice. Carrier signal. To broadcast this audio over long distances, the audio signal needs to piggyback on a carrier signal. The carrier signal is just a steady electromagnetic wave at a specific frequency assigned to the station. In this example, the frequency is 1560 kHz or 1560 on your AM dial on your car or AM receiver. Modulation. The audio signal is combined with or modulates the carrier signal. Modulation changes the carrier signal's properties, specifically its amplitude, to represent the original sound. This modulated signal is then sent out into the air via an antenna. Transmission through air. The signal travels as electromagnetic waves, reaching all the radios tuned to that station. What happens in your car radio? Now, let's shift to the receiver side of the equation, like AM radio in your car. Tuning. When you turn the dial to 1560, the radio focuses on the carrier signal at 1560 kHz, filtering out all the other radio signals in the air like 570, 590, or 1300 kHz. Demodulation. The radio circuitry extracts the original audio signal from the modulated carrier signal. Playback. The audio signal is sent to the speakers, turning it back into the music or voice that you can hear. In our example, the carrier frequency is 1560 kHz, which determines where the station is located on your AM dial. Each station in your area broadcasts at a different frequency. These frequencies act as an unique addresses, allowing multiple stations to operate simultaneously without interference. The ability to tune into just one frequency at a time is what allows your car radio to play only the desired station, even though many other signals are flying through the air around you. The simple process of modulating a carrier wave, transmitting it through the air, and then demodulating it on the receiving end is the foundation of all radio communication, not just AM radio, whether it's a FM music, Wi-Fi data, or satellite signal, the same basic principles are at play. In the next lecture, we will dive deeper into these signals involved in AM and FM radio and how exactly they carry sound. From there, you will start to see how radio engineers have managed to broadcast sound and data over vast distances. I'm Tayfun, and I'm waiting you in next lecture.